cool. So let's we'll kick it off here. Hi, Lynn. I see Lynn has entered. Yeah. So this is great. We have I'm really excited for this one actually, and I know you're presenting on something that's very important, Maryna. And Maryna, for those who aren't familiar, is the ML research team lead at Borealis AI. Her passion is to drive innovation and apply state-of-the-art technologies to solve real-world challenges. So her research interests lie in improving the explainability and interpretability of deep learning models. And Maryna completed a PhD in engineering at the Taras Shevchenko National University in Ukraine. She has previous industrial experience at Amazon in Vancouver, at Sociomantic Lab in Berlin, and at Samsung in Kiev. Outside of work, Maryna enjoys reading, hiking, or boxing, which is very cool. Awesome. So I will let you get to it. And yeah, for those who are joining, feel free to ask any questions in the chat, and we'll make sure to keep an eye on those as well. So with that being said, Maryna, thank you for joining.
Thank you, David, and hi everyone. Welcome to the presentation, Technical Debts in Machine Learning Projects and How to Mitigate Them. So in this presentation, we will not talk about how machine learning is beginning to reshape our world. What we are going to talk instead is about difficulties that we experience when we make research machine learning models like ResNet-50 or Roberta work for real-world problems. Machine learning models in real-world systems reveals how difficult such system can be to debug, test, monitor, and maintain. And the first step to addressing these problems hides in a simple idea. Machine learning is not a software, and we need to stop treating it as such. All examples discussed in this presentation will be hypothetical, but they come from personal experience in the same machine learning technical debt mistakes being made everywhere, in fast-growing startups and in large tech companies. So in this presentation, first we will start by defining what is a technical debt. We discuss why it's essential to recognize technical debts and manage them. After that, we will look close at why machine learning projects tend to increase technical debts. We explore how machine learning systems can become more complicated if they have additional data dependencies or different feedback loops. And finally, we slightly cover common challenges for projects where teams have different background and need to work together. It's not always the case for every project, but not a rare case when there is a clear separation between product, engineering, and research teams. Okay, so let's start with what is technical debt. Technical debt is a concept from software engineering. It talks about how to account for the cost of moving fast. And very often, it's appropriate to move quickly. Maybe we have some product that needs to be launched by someday. Or perhaps we have some potential feature that can significantly improve the experience of our current customers. Or maybe we try to finish experiments to meet deadlines for the conference. So not all debts are bad, but ignored debts will cost us in the future. Projects where technical debts are ignored for a while can be at the stage where the whole team is working on fixing bugs and doesn't have time to develop new features. But before we'll start diving deep into machine learning debts, I want to pay attention to this paper. This was one of the first research papers to highlight the hidden cost of machine learning in academic settings in 2015. It is a great starting point for those of you interested in this topic. It introduces many concepts and terminologies used nowadays in these presentations. However, we should keep in mind that some part of it are less up-to-date. Over the time, we have more and more new tools and techniques that help us to avoid and mitigate machine learning debts. So why we have technical debts related to machine learning projects? Let's assume a hypothetical situation. Our task is to build a spam classifier. If we don't use machine learning, we will start developing some rules to identify if the email is spam or not. For example, we check if there is a word sale in the title, but then we need to check words like buy, discount, etc. As a result, we'll spend a lot of time to develop a lot of rules, and most probably, there'll be many rules that we still don't cover. As an alternative, we can use machine learning model to classify the text in the mail. It can be a simple model like naive Bayes, or more complex model like fine-tuned Roberta. For these models, the behavior is defined by data. Therefore, we can easily build a spam classifier if we have a bunch of spam and non-spam emails. This model will learn from this data. So this is excellent news. Unfortunately, it introduced the first challenge. In traditional software engineering, we can create strong abstraction boundaries using encapsulation and modular design. It helps us make isolated changes and improvements in the system. But for machine learning, we have a new component, data produced by the natural world, and our world doesn't have any prior needs to have any boundaries for this data. New ways to create spam email appear every day. Moreover, some bad actors can even start designing new examples to trick our system. In some cases, we need to consider the possibility of design attacks. The good news here is that bad actors generate such examples with machine learning, so they need to learn how to deploy and support machine learning systems as well. So why changes in the outside world leads to such significant changes? The first principle we will discuss, no inputs into machine learning models are independent. Machine learning models entangle and mix inputs. If you change anything in the input, you change the whole system. This is known as the cake principle. Changing anything changes everything. For example, let's assume that we have simple machine learning with 4 input features, and it is working as expected. And at some point, you figure out that there is a better feature that can be used instead of feature 2. You replace it and you retrain the model. And if you do this, the entire model changes and can work differently. Now assume that you have decided to add a new feature. While you can change a very small part of the model, you can still get a new model with a new behavior. This can be dangerous. You might believe you are improving an input in isolated fashion when the opposite is true. Now imagine another situation. You want to build a spam classifier. You have access to another model, like, for example, Roberta from Hugging Face. It seems intuitive to leverage that work and train a small new model on the Roberta embeddings. The problem with this approach is that it makes the system highly unstable and significantly more difficult to make changes in the future. This is the problem common to any model trained on the output of another model, like model A and B on this slide. Model B has learned the details and flows of model A. Improvements made to A will have an impact on B if it's not retrained. Even then, if you do retrain B and all other models train on its output, it's not easy to assess whether any improvements in the output result from the improvements we made to the model A or due to the retraining of model B. The situation can be even more dangerous. Let's assume that the prediction from a machine learning model is made widely accessible, either at runtime or by writing to files or logs where the other system may later consume it. Without proper access controls, some of these consumers may be undeclared, silently using a given model's output as an input to another system. So we have an issue with potential undeclared consumers like model B on this slide. Undeclared consumers are expensive at best and dangerous at worst because they create a hidden tied couple of model A to model B. Changes to A will very likely impact these other parts, potentially in ways that are unintended and poorly understood. So what we can do to improve our system? First, we can support real-time monitoring for the inputs and outputs of our models. We can monitor the distribution of the input features. We can compare the summary statistic for our predicted labels with the summary statistics of the observed labels. It's not always a bulletproof method, but a simple sanity check. If something is wrong, it can alert you very quickly. If the input changes often and significantly, you may consider retraining your machine learning model more often. Second, what we can do is to use interpretability and explainability tools. Will not solve your entanglement issue, but it can improve your debugging, testing, and monitoring of the models. In some cases, you can even use more explainable model types like decision trees. Of course, if you can solve your business problem without very deep neural network. Another thing that you can check is to validate and improve your model robustness. More robust models are more sustainable to small changes in the output. Therefore, they will be more stable in the production environment. You can also retrain your models instead of using the output of another model. The simplest solution here is just not to use the output of another model. If this doesn't work for you, another option is to create a new model using the transfer learning techniques. This is more powerful and slightly more technical solution. If you cannot avoid the situation when you need to have a pipeline of different models, then always be sure that you retrain your models in order. Also, to prevent us from undeclared consumers, we can create access controls and service level agreement between machine learning model and consumers of that model. This is enforce an explicit declaration and contracts between model and consumers, which remove hidden dependencies. So we know that our model can easily become unstable, and we discuss how we could improve the model. Now let's look closer into ways how we can improve data dependency. So the first potential issue that we can have if we have unstable input data. Unstable input data refers to data that changes over time when there are no changes. It often occurs when, in order to move fast, the machine learning algorithm consumes data directly produced by another system. The input data could change explicitly, for example, when engineering group in charge of the data changes it. The data can also change implicitly, for example, when another machine learning system gets updated. The problem is made worse because such updates to external system can happen at any time. Another dangerous situation that can be missed when design machine learning algorithm is not investigating properly that some input features are more important than others. Sometimes a small fraction of input features accounts for more than 95% of the model's performance. It's common over the model's development lifecycle to accumulate many features, a large portion of which becomes redundant. On their own, these features neither significantly hurt nor help the algorithm. Individually or in an academic scenario, they are harmless, but they can lead to instability with the system and create vulnerability in a larger machine learning systems. So again, with unstable data dependency, a proper real-time monitoring systems can help detect not only changes related to external world, but actually internal changes in the internal system as well. During designing your system, you are not only considering the ultimate accuracy of the model, but the ratio of the accuracy to the complexity of inputs. If you have a small number of simple inputs, there is much lower probability that something will go wrong. If you have features that don't add a lot of value, you should think carefully about whether this small improvement is worth the risk. There are other tools you can use to assess feature importance to help you remove unnecessary features, but ultimately it's a subjective decision based on your needs. Another practical tip is to track the provenance of data in your system. If the version of any upstream process changes, you don't adopt the new version until you update the downstream processes. This means freezing the version of input until you update the whole system. Some tools can help you automate this. Let's now look into the challenges that we have if we build live machine learning system and we update it over time. It can make it very hard to predict the behavior of machine learning model when it's pushed into the real world. Real world will interact with your system and will provide feedback. Detection of these feedback loops is most difficult when the rate of change is slow. They are easy to detect when models are updated frequently. For example, detecting a data shift that occurs directly after deploying a model is much easier than detecting a related data shift that occurs a number of months after deploying a model. While designing real systems, we need to consider two types of feedback loops, direct and hidden. Direct feedback loops occur when the output of machine learning model influence the future input features on which this model is trained. This causes the behavior of the machine model to converge into arbitrarily artificial solutions that perform poorly. For example, if I consider a simple movie recommendation system that recommends 5 movies to all customers all the time, the user, for example, will select one of the movies from this list. And in this case, the user doesn't know about all movies in our database. And even if the user selects some movies, there is a possibility that another movie from our database fit better to user interface. But during retraining, we don't have this feedback to take into consideration. More dangerous is the hidden feedback loop. These are related to direct feedback loops, except the feedback has many steps or feedback happens indirectly, often in unintuitive ways. Let's return to our example with the movie recommender system. And now let's assume that another team has launched another model. And now we recommend to our users top matching movies and recent releases. So this new machine learning model developed by another team can start impact our original machine learning model and in the way that it's a little bit difficult to monitor. So what we can do to improve the model with direct and hidden feedback loops? First, we can use an algorithm that explores new solutions and exploits existing solutions. Such algorithms search for new solutions by trialing outputs that typically will not recommend, then adjusting its behavior based on user feedback. This allows the classifier to land on the optimal solution and avoid the degrading feedback loop. You can also check independence assumption between models if multiple models are deployed side by side or impact each other. You may consider put limits on real-world decisions that can be made by machine learning system. If you are building systems that can negatively impact human lives, you may think where your machine learning system has the potential to be wrong or biased and consider putting limits on such real-world decisions. This leads us to the final form of technical debt created by machine learning that I want to discuss today. It's cultural debt. When moving from an internet company to a machine learning company, there is a shift that needs to occur, and this is inherently a cultural shift. When you set about testing a website, the process is inherently deterministic. When you use a website, it's immediately clear if it works or not. Machine learning, on the other hand, is probabilistic. Instead of writing unit test and integration test, you now need statistics and probability to check if things work. These new perspectives should appear to the sales team, who need a new approach to know how to demo and to sell the product, to the quality assurance teams, who need new statistics and probability to test the product, and all the way to the leadership team, who need to make decisions for the company in the face of new world. Scheduling regular meetings between business, engineering, and research teams will help understand every side's challenges and perspectives better. So thank you for your attention. I'm happy to answer any question you have. I also want to mention that we have open full-time positions and enrollment to our summer internship, so don't hesitate to contact me after the presentation. Thank you. Okay. Okay, we have a few questions. What interpretability explainability tools does Borealis use? So it depends on a project. In Borealis, we have computer vision projects, we have natural language processing project, time series forecasting. Therefore, I think it depends on a particular use case that you have. So it's probably better to answer like talking about, so if you need to use interpretability, explainability tools and you want to talk about this, don't hesitate to contact me. We can talk about your use case and talk what is a better fit to you. Another questions, what skills should someone new to the field develop to be successful in the future? It's a great question. Thank you for asking. Of course, there is like, I can say there is difficult to say what skills you need to develop. Like I particularly, for example, at some point work in computer vision problems and thought that I will spend the whole my life trying to solve computer vision problems. But then a new opportunities appears in life and I start working on recommendation system. And then later in life in natural language processing. Therefore, it's difficult to predict which skills you definitely need for your career. So you can probably, so my advice will be start practicing. Started to enroll in some internship or do some particular projects and started exploring what you actually need to solve in this particular problem. Because it can be different compared like the ones that we need to, knowledge that we need to solve computer vision problems or natural language processing. And deployment can be also different. So if you're interested in developing engineering skills, it also can change, depends on the area of machine learning. So the advice will be, don't hesitate just to practice any skills that you already have. Okay, the question, you touch on features hurting the model when outside of research environment. Any tips or examples of ways to assess feature importance or approach that if you are not sure which features? Okay. So first of all, like sometimes we have problems when can have potential to have biased features. For example, if you develop a news recommendation system and you can consider to use some features related to your user, for example, a gender of the user, right? And as a result, you end up probably even find a content that is better fit to the user, but it can have more difficult, more dangerous feedback loop, because you can start showing to this particular user only the content that is fit to their interest. So you can actually accumulate the bias that is already exists in the society and only make the situation worse. I hope, David, it's answered your questions, because it's like really like we can talk a lot and dive deep into this. What you mentioned about data lakes and continually growing data sets. Versioning is the way to help, but as the data version change over time, version 1.0 becomes very different from version 3.0, especially avoiding leaks in the train test splits when comparing a model's train on version 1 to version 3 test set. Is it worthwhile to still compare against older version of the data, or should you discount it and only analyze the latest version of the data? That's a good question. So probably it also depends on your business use case. Let me find some examples here. So let's assume the data contains some behavior of the users, right? And you already have a solution that is working. For example, you predicting movies, and you definitely know that your recommendation system works really good. Then when you find a lot, like, let's return to our examples with hidden feedback loop, when you launch a new model and you add additional feedback loop to the website, therefore you started getting new data. And probably when you retrain the model or start training a new model in this scenario, you will get completely different feedback loop, and it makes sense to retrain it. But what I will do here, like I will separate probably and brainstorm which tests and monitors will be still the same for the old system and a new system, and some which will be new to the new environment changes. Because, for example, you can still test if there is like some amount of users that click on your movie, right? Will not change when you move to the new model. And it's sometimes in some situations, it helps us, like these sanity checks help us to avoid really serious situation, like really stupid situation. Sometimes like the system can be so complex that you test it multiple times and then you go to production and it doesn't work as expected because some did some mistake during the deployment, right? We're all human beings, we do some mistakes. So having some simple sanity checks, it's important. And I think if you're still working on the same system, it shouldn't change if you go from one version set to another version set. But considering the training, because you have a new version set, probably you have a new user behavior, it's also something to consider. I hope, Jordan, I answer your question. Thank you, Sergey. Guys, any question here? Here is a great question from Dmitry. What kind of practical machine learning pipeline tools you probably use in Borealis to reduce technical depth? Do you have separate people, MLOps, to help with this? Yes, we have separate people, MLOps, to help with this. And in the company, we have a separate team who is called platform team, who's actually trying to help us to set up proper pipeline that will help other teams, right? So a lot of, as I said, we have different projects in Borealis AI. We have different specific, like project-specific, different details related to every project, but there are a lot of commonality, right? All of them have the same kind of need to get the data, version the data, run some experiments, and deploy the model in production. Probably it will be like maybe online inference, batch inference, but there are a lot of commonalities. So the company invests a little bit in a team who try to build a common platform which can speed up all projects to move faster. And this team looks into both into the tools that exist and tools that is missing for our use cases in particular, and try to develop them. And like there are a lot of them. So I will like kind of, first of all, probably if you consider like how to build it for your use case, I probably will start answering the question if you can work with tools that is working in the cloud, or you probably is not allowed to work in the cloud. Therefore, you will have you will look into the slightly different tools, right? So for example, I had experience using Amazon SageMaker. It's a great experience. It provides you a lot of interesting stuff that you can work and speed up your experiments, but then you couple with AWS. So if you can be coupled with AWS, probably you want to consider this. If you are not coupled, you can try, for example, MLflow for your experiments. And in this case, this is open source tool. You can set up into your machine, in your own machine that you run your experiments, or probably somewhere on the cluster, something like this. So there are a lot of them. I agree with them. I agree, and there is nothing, like there is no one that will solve all use cases. So probably you need to look into your use case and try to find the one that works best for you. So, but if you're right now like kind of trying to understand what is to select, what is to use to your particular company, then just probably find someone with more experience that you can discuss pros and cons and find out something that fit to your use case. I hope I answer your question, Dmitry. And don't hesitate to ask follow-up questions, because these questions are really good. I can talk a lot and dive a lot deep into them. And that sometimes there is no great answers, right? We have so many different use cases, and not necessarily the solution that works for one team will work for another. Okay, looks like no questions. All great questions. Thank you, guys. Thank you, Faraz. Thank you, Madison. Thank you, all of you guys. Thank you for your time. And I wish you enjoy the rest of the meetup. Bye.